So here it's going to be kind of mathematical, but I'm going to try to make it like minimal. Okay, so the first search that we have, like usually you're going to do like a regular data scientist with no AutoML system is going to use either grid search or random search. The problem with the grid search is that you only search the point on the grid that you define. So you might waste a lot of time on points that doesn't have any meaning. I mean, it doesn't help you. And also it's exponential on the number of parameters. So it's going to take you a long, long time to search because there's a lot of combinations. The problem with random search is basically that you don't learn from history. So you just travel around the models and you're going to waste a lot of training on points that are not relevant. So both of them are what we have. Like random search is good because you can do, if you have a parallel system, you can cover a lot of models, but still most of your computation is wasted. So the field of research in AutoML come up with, this is the base model, which is called sequential model-based optimization. Don't know if you heard about Bayesian optimization, but this is the definition of the problem. So because it is model-based, what we do is we choose a surrogate model, which is the Gaussian process regression. And what is special about this process is that it doesn't give us a point prediction, but it gives us a Gaussian distribution prediction. Okay. So what we do in the search, and then in addition to that, we're going to make prediction after each trial, and then there's something called an acquisition function that's going to score the prediction, and this is a Bayesian acquisition function, and then it's going to give us the best point to search next. Okay. So if you see here, like in this first iteration, we basically made the search. We evaluate the function fx into observation. We use the Gaussian process model to make this Gaussian prediction. This is like the mean, this black line, okay? And the dotted line is our real function, okay? And then we use our acquisition function to score this score our all of those Gaussian function or Gaussian scores. We got the best point here. And then in this iteration, we run another FX, we run another evaluation, we update the Gaussian, and we run against the acquisition function. We got the best point. Now, we see that the acquisition function is moving between exploration and exploitation, which means that at the first phase, the first phases or the first 20 models, the Gaussian process will look like random, okay? Because it doesn't have it's gathering information about the function. So it's kind of exploring the space. And then it moves into exploitation. So it kind of like know where is the minimum. So it's kind of start getting experiments near the minimum, okay? And everything like that is up to a budget, of course. So budget can be a CPU time or actual clock time, etc. or cost, okay?